The demand functions from Cobb-Douglas utility functions are homogeneous to degree 0. Let's show that. So here we have a general Cobb-Douglas utility function. We got units of good X and units of good Y. Here we have the consumer's budget constraint. M is income. We got the price of good X and the price of good Y, and each are being multiplied by units of the respective good X and good Y. We're going to set up Lagrangian here to get our first order conditions. So we will get the partial derivative of the Lagrangian with respect to good X, and we get this partial derivative result. The a on the exponent comes down in front, and then we subtract 1 from the exponent on the x term here. We set that equal to 0, this result. And we get the partial derivative of the Lagrangian with respect to good Y. Set that result equal to 0, and then one more partial derivative, the partial derivative of the Lagrangian with respect to lambda. We just get that the constraint. From this partial derivative of the Lagrangian with respect to good X, I'm going to solve that for lambda. So that's this equation right here, solve for lambda. I do a similar thing for this second partial derivative, the partial derivative of the Lagrangian with respect to good Y. I solve that for lambda. I will set both of these lambda equations equal to one another to eliminate the lambdas. And from here, I'm going to simplify this down and solve it for good Y. That will allow us to get the demand for good X eventually. So simplifying this for good Y. So what I did here is I divided through by x raised to the a minus 1 power. So that's why this is over here now. And then on the left-hand side, I divided everything through by y raised to the b minus 1 power to get this result. Rewriting that result from the last slide. Following the rules of exponents here. This y term in the denominator I'm going to bring up to the numerator to get this. And this x term in the denominator, I will bring that up into the numerator over here. Okay, this left-hand side over here in the numerator, that's just going to simplify down to y. Likewise, the right-hand side in the numerator, we're just going to get bx. And then finally, I will multiply both sides through by the price of good X to get this result right here. I'll take this result and I'll plug it into our budget constraint. So in our budget constraint where I had Y, I will plug in what Y equals. And you'll notice that the price of good Y terms will cancel. So I get rid of those. I'm going to divide through by the price of good X. So dividing everything through by the price of good X leaves us with this result. On the right-hand side, I'll do some factoring. So factor out an X term. On the right-hand side, in parentheses, that'll just simplify down to this. And finally, the demand for good X will equal this result right here. So again, the demand for good X will look like this. And now we're going to check to see if this function is indeed homogeneous to degree 0. So I'm going to multiply each variable over here by alpha. So income and the price of good X multiplied by alpha. That will simplify to alpha to the 1, bring this alpha up into the numerator, that's alpha minus 1. So notice here alpha is really raised to the power of 0. So here we have an example of a function that is homogeneous to degree 0. So the demand equation is homogeneous to degree 0. This would be consistent with this notion that if we were to double income and prices, the consumer's choice would be unchanged. Okay, that's it. I hope you found this video helpful.